I'm currently a resident at Meta. So today I'll be sharing a talk on-device ML and efficient model training, aka how do we make models efficient, how do we make it small enough to actually run on devices. So before we start, I just want to apologize in advance because I got a cold a few weeks ago, so you might hear me cough during the session. So sorry about that. And now let's look at the agenda for today. So here we have basically three components. First, I'm going to introduce you, just ease you into what is on-device ML. And then I'm going to talk about how do we do the efficient model training and inference, basically how do we train it and how do we do the testing, like making sure the model actually performs really well. And then there are some learning resources at the end of the slides. You can go search or just look into all the online resources, like there's some webinars or open source classes. Because it's Open Science Data Conference, so obviously I'm going to share some code snippets or some links for you to go through at the end if you're interested. And then at the end of the session, I'm going to have a Q&A. So any questions we have, we're going to answer in the end. So first, just let's look at what is on-device ML. You might have seen this in your daily life, but you have never thought about it. What is actually the on-device model or on-device machine learning model? So actually there are many types of on-device ML. So just for a few examples, the first one is this TikTok filter that some people might have used. So basically any filters that you're using, I would say pretty confidently at least 80% right now. For example, Instagram, Snapchat, or TikTok, some models, some filters they're using right now, they're actually just the on-device ML model. Because you can see that when you are holding your hand in front of your face, actually the features or the effects are not going to go over your hand. Versus a few years ago, or at least a decade ago, the old filter will basically just like a mask put on top of video feature. But because ML model has advanced so much, you can see they are optimized or they are catered to your own facial features or your own facial structures. And we can say it's a version of image recognition or facial recognition ML model that runs on your device, which is your mobile devices. And then there's another type, which is more text-based, which some people will say is NLP chatbot or NLP model. You might have seen some of my videos in 2022, 2023 that people are talking to their own AI system or AI chatbot using the Snapchat filter or Snapchat effects. So basically this version is also on-device ML because it also runs on your device. It's an in-app feature. And for this one, you can see that it's actually an NLP model that runs on your mobile devices. And next one is very obvious. We have Amazon Alexa. This one is obviously more the audio or ASR assistant. You say the wake word like "Hey Alexa," and then they're going to respond to your next command, like play a morning playlist or order me some Amazon Fresh. So that's also a different type. So you can see that so far we have seen the three types. We have the video, we have the text, also we have the audio. And next one is also a little bit more interesting. So this one is the TensorFire. I added the link here so you can go and look. So what is this? It's basically, you can see there's a webcam, there's a live feature. So it's more on the video-based type of ML model. So right now there's demo that users it's playing this game called rock, paper, scissors with TensorFire and using the webcam. So it's doing this in real time. And you can see that there's multiple rounds you can do. You can get the results in the real time. And there's a game strategy. So this one is also, I would say it's also image recognition based ML model. And sorry. And next one is also a very popular example. We have Apple Watch. You can see that there are multiple features that's available in the watch. You can see there's some health or health care features that are monitor your health, heart health, anything, and they're going to show you the trend and maybe give you an alert if there's something below the actual stats or numbers. And then we also have Tesla Autopilot or the Waymo or Cruise. So especially if you live in the Bay Area, if you go into a city, you can see that there's multiple type of self-driving cars driving around, like Waymo or Cruise. So for this one, it's really interesting because you can see there's a there's a camera on top of the car. Sorry about that. What it does is there are multiple cameras in front of the car and the car or on top of the car, and they're collecting all the images or the video images in real time of the surroundings. And then the ML models that's equipped on the car is going to do some processing in real time, and then give them corresponding feedback. So do we go left, do we go right, or do we stop if there's something in front of us? So this is also a type of on-device ML, except for this type, the device is a car versus a mobile device. So in summary, we can see that, I'm sorry, there are multiple type of devices we're talking about. We have we have mobile phones, automobiles, and smartwatches. And also we have home devices or laptops and many more. So basically we can see what is device. So if the device have certain type of computing power and certain type of memory storage, then we can use it for the on-device ML training. This is really interesting because if you're taking some classes at school that basically allows you to do the Raspberry Pi, you can see just a really small electronic board can be seen as a device that you can use for training. And actually it's really interesting because a lot of cloud computing classes or a lot of on-device ML classes at universities, they're using Raspberry Pi as a device because it's really cheap and it's really efficient versus like buying some device computing resources. So here's the first part. We just get a gist of what is actually on device. And now we're looking at what is the goal of on device and why do we do it? And if there's any limitation. So first one is it's pretty straightforward. For on device ML model, we want it to really make it really fast. We want to perform inference on the models directly. Meaning we don't need to upload anything to a cloud or remote servers or anything. So the goal of on device is we want to do anything, like everything on the device because it's low latency, it's very private because data security is a massive concern in the AI community right now. People don't want to give away their data because obviously it's their personal information. So if we do the on-device ML, we don't need to upload anything to the cloud or to remote servers, and we can complete everything in the offline work mode. And then there's really interesting or really efficient one is we don't need to pay the cloud computing bill because if you have work with AWS or Azure or any type of cloud, you know it's going to be very, very expensive, especially if you're running multiple clusters of GPUs or do the parallel computing. It's going to be a huge cost. But also, we know that if there's a pro, there's a con. So for on-device ML, there's a few that we really need to look into. So first one is limited computing resources, which is very obvious because compared to the cloud or any other remote servers, the computing power of devices like mobiles or laptops, they're very limited. Constantly you need to charge your device or you need to connect it to a certain type of I'm sorry, you need to connect it to a certain type of charger or doing resource upload. And then there's also memory, storage, power consumption. So that's a con. So here we are going to look at how do we actually do the model training. So how do we make it lightweight? Because we know that if we're having a very limited computer resources and memory, there's going to be a performance degradation. So even if there's a performance degradation, we still don't want to lose at least too much of its performance. So here we have a few techniques we can look into. So first, quantization, pruning, distillation, and neural architecture search. So I will go into each one in details in the following slides. So first one is quantization. So for quantization, I'm sorry, a lot of people have heard of it. So it's very common and popular technique in ML community. So for anyone who's not really familiar with it, you can say the process of quantization is basically do the mapping of continuous infinite values to a smaller set of discrete values. And why do we do it? Because we want to make it more lightweight or reducing the computing and memory costs. And how do we do it is we are basically converting the data types, and we're using the low precision data types like int8 versus FP32 or FP16. Usually in ML community, or at least in ML training, there are multiple data types we're familiar with. And here's the documentation on how to do quantization in PyTorch. So anyone who's interested can look into it. So first, let's do a refresher course on what is the common data types we're using in ML training. So at least for AML, you can go to the third line. We have FP32, int8, FP16, FP64. So most of the times, the top three, which is FP32, int8, and FP16, are the most popular ones in quantization or do the ML training. Sometimes they're also using FP16, but at least for ASR, they're not as popular as the other data types. And the top two is very obvious. FP16 and 32 cost more memory than 16 int 8, but they're also more accurate. And performance-wise, similarly, FP16 to 64 will be costing much more memory, and which means they're going to rank lower in the performance rank. And then lastly, we have the scientific calculation. So this one is not really mentioned in the ML training or AI training. So this is just for anyone who's interested. If you are mostly doing the ML training, you can just look at the top 4 lines. And when we're talking about ML quantization or AI quantization, we're mostly talking about FP32, int8, and FP16. Sorry. So first, let's just look at 2 examples. So you can look at that on the PyTorch documentation or TensorFlow, any type of ML framework. Basically, there are 2 types of quantization we're mostly using. First one is called post-training state quantization. So this stands for PTQ. And what it does is PTQ will quantize weights and activations of the model. And then we're going to fuse the activation into the preceding layers where possible. So it's usually used when we have both the memory bandwidth and compute ceilings are really important. So here's the diagram of how do we do the actual quantization using the PTQ. You can see that the original model, we have that P32, and we have the weight, and then do the linear to the activation and the next layer. And when we're doing the state quantize, they're all in the int8. And the next one is QAT. So QAT is much more popular in at least in the quantization for ML models. So when you're looking at a quantization, most quantization in ML are preferred using the QAT version versus PTQ. What is quantization aware training? So for QAT, it's a little bit different because the model quantization has happened during the training, which means it allows more accuracy. Because QAT we can do in using the static quantize or dynamic quantize, or just for the weight only quantize. And during the training, all the calculations are done in the floating point with fake quant models, modeling the effects of quantization by clapping and rounding to simulate the effects of int8. So here you can see the QAT is actually using something called fake quant. So if you go to the code base of PyTorch or any quantization library, you can see there's some data type or there's a variable that's similar to fake quant. That's basically helping the process of QAT. And then you can see at the end, after the model conversion, weights and activations are quantized, and then quantized activations are fused into the preceding layers where possible. So this one is a little bit more tricky or complex than the previous one, but QAT is preferred. because it's more accurate. So now let's look at an example on how do we do the actual QAT. So here I took an example from PyTorch. You can see that it's a very simple ML model in the class M. And how do we do the actual context? You only need to remember 2 steps. So first one is you need to convert any operations that require output recognition from functionals to model form. That means you can look at in the int part. So you need to convert any layers from nn functional dot something to torch nn something, making sure everything in the model form, which can only be quantized. And the next step is to specify which parts of the model need to be quantized. So because in QAT, you need to remember one thing, not everything can be quantized. This is especially true in the very complex models. For example, if you have a model that's 60 layers, and for each layer, it's constructed using, for example, maybe one LSTM layer, one linear layer, and then some customized layer that you built yourself. That usually means because for QAT, you need to at least modify the code and perform quantization in the code base yourself. If you haven't done so, most of the times you can only quantize the linear layer and LSTM layer, because for most of the models, you need to look at the redistribution to see if it can actually be quantized. And for any layers that can be quantized, the next step is you need to assign either the qconfig attributes, or you need to specify the MIP. So here you can see, sorry, here you can see we are assigning the qconfig in the model, and then using the function, basically we're attaching one global qconfig, and inside the config we are adding all the information that's needed to perform the QAT or the quantize. And for this part, it's really tricky because the quantization effect or performance really depends on your mobile devices or your training devices. Also depends on what is your hardware. So it doesn't matter if you're running on using cloud or using GPU cluster or using your mobile device, because there's a difference between different hardware. So you need to really look into what is the supported model backend. For example, there's this one tricky one for mobile inference, which is QNPAC. So if you're using that one, you need to specify it and also look into any corresponding features or parameters you need to update. And there are multiple combinations. So in summary, just here's just one simple example of how do we do the quantization. So first one is we need to specify the model type, which is here, and it needs to be in the model form, so it's in something. And the next step is to specify which layers can be quantized and how do we actually want to quantize it. Also, there's some data types, some layers to quantize, and in the end, we fuse it and convert the model back into some data type. Most of the times it's in date. So here's QAT. Just for a summary, so for now we look into the first technique, which is quantization. We look into PTQ and QAT, and QAT is more popular or more commonly used in on-device ML, or just basically any ML training. And there are also some data type. There are some really interesting types. For example, lately NVIDIA published a paper on FP8, which is a different type that can be used for quantization. It's more lightweight. And there's also BF16. So anyone who's interested, you can just look into it. And next one we're looking to pruning. So pruning, sorry, pruning as the name suggests is similar to pruning in graph. It's basically a data compression technique, and it helps us to reduce the decision tree by removing certain type or certain section or component of the tree that's not really helpful in the long term, or it's kind of redundant, or it's not as important as other components. And in ML pruning, basically, you can look into as we're removing the model parameters. Sometimes it's individual parameters or in groups, such as neurons from an existing network. So they're more lean, but contains much more important information versus a more complex, but really hard to read model. And next one is distillation. So this one is also very popular, also widely known for model distillation or knowledge distillation. There are multiple papers on this on this part. So usually for distillation is we can combine it with other techniques such as neural architecture search, which I will cover later. And it's a very common technique, and for anyone who hasn't had the background, it's basically we're distillating the large complex teacher models into smaller student models or smaller models. And sorry, and there's some dataset distillation algorithms. Basically, we're optimizing the dataset using the loss function from the kernel regression. This is just one example. There are multiple types available. So here you can see that it's a very common data set using CFR10 image data set, and distillation allows us to just using one sys2 data set using only 10 synthesized data points versus 50K, which will significantly speed up the ML training and inference process. So, which is also why people are combining a lot of the distillation process with other ML training. Sorry. And then next is the neural architecture search. So this one is also not a new technique. It's been around for, I would say, since at least a few decades. But it has advanced rapidly in the past few years or past decade because the emergence of different ML models, especially for the models with a lot of like large size parameters. So I'm not just talking about the large language model. I know it's been around, it's very the hot topic this year, but also just basically any model or any complex ML model with large scale parameters. So you can look into as a technique for automating the design of artificial neural network for a given task. So if you convert it into the actual ML task, basically we're building a combination of networks that shares the weights of the given neural network. So basically you can look at neural architecture search as a process to build a weight sharing graph where each model will be a subnetwork of the given network. And then when we do the training using the neural architecture search, as the name suggests, the process is actually just coordinating the updates on all the subnetworks. And we do this iteration for multiple times. In the end, we'll be optimize a single set of parameters to ensure that all the subnetworks will have really good performance at the end at the same time. And interesting thing is neural architecture search can be adopted in many tasks. So it's common ones include the computer vision, NLP, or speech recognition, or just even in reinforcement learning. Here you can see it's just for one CNN tasks. We have a, you can see it's a feature map with different channel numbers. And then here's just the distribution of channels. And then inside the neural architecture search process, we have different layers or different processes of the prune channels that can be shared between different subnetworks. And next one is how do we have an overview of neural architecture search? So here is a graph for the process workflow taken from one of the recent research papers done on how do we do the neural architecture search, because it's been around for at least few decades, because so there's many iterations on the architecture or the NAS process. The most important component, first one, is the search space. So search space is we are defining what is the model architecture that are used for searching, and what is the number of iterations during the neural architecture search in the process, or what is the size of the model, and how do we do what is model architecture setup. So you need to define everything in the search space, and then in the search strategy, we do the multiple iterations of the searching. In the end, we'll return the performance estimation to the search strategy, and we do this iteratively multiple times. By definition, in the end, will give us just a performance estimation or just an expected result. And sorry. And then next we have just to look back on how neural architecture search has evolved in the past 2 decades, because NAS was first proposed in at least in the late 1980s. But because there's multiple evolution with our algorithms were just different model types proposal, there's a rapid increase of NAS related papers. First, we have the latest progressing evolution is from 2019. You can see there's a almost double or triple the number of papers. And the latest years, there's multiples on NAS research papers in different fields. So anyone who's interested, you can go look into the research paper. And here's just a recap. We have the search space, the component that's most important. You need to define everything here. And which means that a lot of the search space are very task specific. So you cannot just use one for another task. And to get the optimal performance, a lot of times you need to do the trial and error multiple times to get the optimal result. Also, there's a difference between the sizes search space and the number of iterations we're going to perform in NAS, because we need to find the optimized solution, but also we don't want to waste a lot of computing resources. And we know that because we're doing the weight sharing graph of multiple subnetworks. So it's going to be very resource consuming. Here is just an example of search spaces of how do we construct it, what is the type of graph. Is it the directed acyclic graph, or is it chain graph, or duplicate styles? So there are multiple types, and you can always tune it towards your own liking. But basically, there's just 4 summaries of the NAS search space. And next is, even for neural architecture search, there's still some optimization techniques or search strategies, because we know that for different search spaces, we can treat them as a different type of graph or resharing graph. So combining just for a few, just here for first thought, you can just look into it yourself. We have evolution or Bayesian optimization or Monte Carlo tree search. And baseline, just for the mention, is it's random search, meaning that architectures are selected randomly from the search space, and then they're fully trained. So the architecture with the best validation accuracy is output in the end. And here, actually this year, there's this really interesting white paper done on the neural architecture search. The authors read into at least 1,000 neural architecture search papers and given us a summary. So here's the link. And because our time is running up, so I'm going to a little bit quicker in the end. So here is the next technique, which is hypernetworks. So you can treat them as something similar to neural architecture search. It's also a weight sharing graph, you can see. And what it does is, you can see it seen as a neural network that generates the weight of other neural networks. And inside one hypernetworks or inside one supernet, there are multiple subnetworks combined together. And then we do the multiple iterations update, which will give us a different type of models or different type of subnetworks in the end. So here just the one example for the process. So we're almost at the end. So here is just an example of all the on-device AI frameworks that you can use. I would say at least some of the frameworks are not actually actively maintained, but you can use it still to build your own device, your own apps, or own models. But a lot of times people they're just using PyTorch and TensorFlow to build their own on-device ML. So there's no difference. Just here, just for as an example. And lastly, we're talking about the inference. So inference is pretty quick introduction. On-device inferences, we're just making the predictions using the tree model with real-time input on device. And obviously the pros is there's no uploaded data, so every data is retained on your own device. And if you want to purge it, then they're gone, so no one can get hold of it. So lastly, we have some learning resources for anyone who's interested. This one so all the links are very intro level courses to just get a gist of what is on-device machine learning. They're still rapidly evolving, but basically you can see there's multiple tasks you can go into, multiple field research. Also a lot of them by schools and tech companies. And there's some research papers and books you can look into. So let's look into the Q&A. We're not taking too much time.
Yeah, there is one question from Daniel.
Sorry.
Do you see that, or would you like for me to read it out loud? How it's better for you?
Maybe you can read it. Sorry.
Sure. So Daniel asks, so is this NAS search method kind of like Monte Carlo analysis? Also, where along the neural network pipeline would one implement their own algorithm?
Okay, so two questions. So first one is the Monte Carlo analysis. I wouldn't say so. If you want to mention Monte Carlo analysis or any analysis in the combined with NAS, we usually are doing this using as an optimization technique. Your architecture search is basically look into as an inference setup. So you have your own model. Doesn't matter what type of model it is. It can be transformer or RNT or any latest ML model or your own customized one. And then you set up the training pipeline. So this one is more on the ML inference side. You can using either Python or C++ to write your own training pipeline. We basically start as a graph or search space. So it doesn't matter what type of model it is. And then you do the update using the search space. So for search space, a lot of times you need to configure it yourself. So depends on the type of task. So for example, in ASR or in a lot of training, basically you're defining one JSON file with a lot of inputs. So what is the layer name? For example, model layer 1 FFN model.0. So that is, you need to list everything in the search space. And then the code, the setup NAS framework will just read into it and do the update according to the configuration. So which is why it's really important to set your own search space, your own configuration. And so to answer your question, doesn't matter what type of model you use. You just define the model in your own model setup, and then you just link it using a configuration file so they can do the search.